Alright guys, so we would like to do some static analysis with using CATIA, and we start with having two parts of elements. In this case I've already prepared two part, a bracket with stiffener. So if I open this L bracket 2 file, you can see I have this part drawn like a L shape with two holes here. And next part I would like to show is the stiffener, and the stiffener is actually an element that I will put in between these two plates here. So in the middle, to be exact. So to say that it is a stiffener that will support the load that is being exerted on the surface, and by having this stiffener, actually it's supporting the load to distribute through the stiffener and going through this another part, so that the bending of this plate will be reduced compared to without stiffener. So we'll see on how the analysis after this. So let's say we start with the basic analysis without the stiffener. So I show you how it looks like. So we say now there's a warning here: material is not properly defined on part 2. Yeah, I didn't assign the material first, but of course I will do it afterwards. So I click OK on that, and we have this new analysis case. And we'll start with static analysis for this case. So firstly, as what is being worn there is no material. So firstly we would like to we need to assign material here. So I click on the link manager, open the tree, and go to the part body, make it highlighted, and then you can see orange lines are switch on this metal or this material or this part. And then we choose this button material and look for it, and just click on the material on this connection. Yes, as finite element analysis involve the material properties, the Young modulus value, the density, the Poisson's value, and others. So we start where looking for the material properties. So in this case I would like to use aluminium. So this is classic example. Normally people we have aluminium at in our laboratory or in our workshop. So why not we choose aluminium to look at the effect. If you want to look at the aluminium properties, I think can look it here. Yeah, we have to double click on this, and it will change the template here. It is now in part design setup. Okay, and then after that you double click on the aluminum again, so we can go to analysis. You can see these are the material properties. So the material is isotropic. What does it mean? So it means that the elements are being distributed constantly with the Young modulus value for aluminium is 7 to the power 10 Newton meter square, Poisson ratio of 0.346, the density is 2710 kilogram per meter cube, and thermal expansion as shown here, and the yield strength. So these two are very important in material science, and the other are other materials used to define the volume of this material or part. Okay, so click OK, and we come back to the analysis manager, double click on this, and can close the tree for the manager. Next, I would like to show you a simple basic analysis, static analysis. So we start with the clamping. So where's the clamping? Clamping is the constraint. So we search for this restraint example at restraint toolbar. So after that, take out this clamp, and I will yeah, select the circle or the hole here by clicking by selecting that hole. It's what I mean is it looks like we are clamping the bracket through the wall by using for example our bolt or a screw that is being fixed through the hole. Okay, so that is why I clamp the hole there. Next, of course, that's all for our constraint definition. The next step will be the load. So finite element analysis, we need a load, we need the material properties, and then we need the clamp, which is the what we call this as the boundary condition. If you still remember in our past lecture, maybe in your mechanics of material or in your dynamics, there is this differential equation, ODE. You need this boundary condition to solve the simultaneous equation when this equation equals to x, and when x equals to 0, what is y, or when y equals to 0, what is x. So that is boundary condition. So by selecting by assigning clamp here, we are actually giving the equation to be solved properly. Okay, so enough talking about that, and I would like to select distributed force, for example, and then click on the surface of this clamp, and make sure that you see this line. So this line means that the force direction is in this y axis, so it doesn't make sense, so we have to change the direction downwards, and the downwards direction is in the z axis, so we need to change the value here into z axis. But of course the z axis is 10,000 Newton positive. It means that it's going up, so we want to make sure that it does show in the negative direction, so we put negative down in the column. Okay, so if I want to stay with this 10,000 Newton value, I just click OK. Alright, so of course there are a lot of other definition you can make. For example, in finite element analysis, we will mesh, or we call it with splice, or we want to change the solid, or not change, to aggregate or make the solid into smaller atoms. So this is people call it mesh in finite element analysis. So the mesh has its own size, type, and so this is how it is being viewed. If you double click on these nodes and elements, if you open the 3 nodes and elements, you see this 3 tetrahedron mesh. So the only type of element in CATIA, it is tetrahedron. So if you double click on tetrahedron, you will get these windows, and you have the size. So this is the size of the element, and the absolute sag. Absolute sag is the ratio between the two adjacent lines of this tetrahedron. So you can see this is how a tetrahedron looks like. It is actually like a pyramid, but without with the base is in triangular. So it's not a cone, because a cone, the base is circular, but this one is triangular, not a square. So this is what we call it as tetrahedron. Okay, for this time I don't change anything about the size and the sag, and just accept it. So click cancel. So with that definition, it's really enough for us to run the simulation. So before I start the simulation, you have to find this toolbar, computation. You have to find it. It's a calculator shape button. So just click on the compute and select all. In this case, we don't have any other cases, so just click all, and make sure the preview button is tick. So just click OK. It will automatically compute compute your meshing and the boundary conditions, and you get the computation resource estimation. It's about 0.6 second only of your CPU time. And then just click OK, so the computation will begin, and yeah, voila, finish. Next, what we can see is the post image. So what happened just now is the pre-processing, and now this post-processing. We have to find this toolbar image. Okay, so just click on the three button here. So we start with deformation. You can see this is how it looks like. So it's simulating the result or the effect, the after effect when you put load on the surface, and then what will happen. So this is according to mechanics of material, or in the class of static, for example, mechanics of material, or even in machine design. You will see this theoretically how it calculate, and this is how it deforms. So finite element analysis is simulating the after effect when it deform. Okay, so next one we can look at the von Mises stress. So the von Mises stress simulate the location of the highest forces, or the location of force distribution on the element or on the part after it being after the load exerting on the body. Okay, and lastly you can also look at the displacement. Okay, so displacement is consecutive with the von Mises stress. Von Mises stress is the definition of von Mises stress is the distribution of forces and load on the body, while displacement is the displacement or the distribution of displacement. So it's also learned in mechanics of material. When you pull, or when you press this part with the support on there, of course we will expect that at this particular corner, or at this edge, it will bend. So it's starting to bend, and the color image here shows the shows you the firstly the bending is higher at this place instead of in comparison to this location. So it's also can be seen through this legend. So I started with this legend first. If you click on the legend, it will disable this part first, and yeah, you can move this by using your middle button mouse. Okay, so you see the highest value of displacement is recognized by the red color, and the lesser one, it's 0 millimeter displacement, is the blue, the dark blue. So if you come back to this von Mises stress, you can also see the von Mises stress value is highest at 2.84 10 power 10 Newton meter square, and it happens exactly here at this point, 2.84. So this is also logic, because we don't have any support between these two surfaces, so you can expect that the force will exert here much, so the bending will make sure that at this hole the stresses will the total stresses will accumulated at these sharp edges. Alright, so that is the first simulation.